So welcome to our final part of lecture 31. The goal in this part here is to prove this particular theorem, namely that if we have a linear map from V to W and we know an orthonormal basis of V and W, then there's a relationship between the matrix of the adjoint and the matrix of the original linear transformation. And that relationship is the adjoint, the complex transpose of the original matrix gives you the matrix of the transpose. Okay, so I've written this out in the special case. We've already talked about this. If we use the standard basis of Fn and Fm, really what this is saying is that if you had taken the matrix of your original map and then figured out the conjugate transpose of that matrix, what you're getting is the matrix of the adjoint. And if you're confused about the definition of the adjoint, so let's go all the way to the beginning. So this is the formal definition of the adjoint. So as we kind of saw, the definition is kind of complicated, but one way to think about what we're doing is saying that, hey, if you have a linear map from V to W, it has a matrix in an inner product space, take the conjugate transpose of that map, that gives you a new linear map from W to V, and that linear map is the adjoint. So really, when you're talking about the adjoint, you're talking about the map that comes by taking the complex conjugate, or the conjugate transpose of the original matrix, right? So just to kind of reinforce this, right, with this example right here, I could have gone from this is the map, here is the matrix. I could have figured out the conjugate transpose. I could have figured out this matrix and then use that to define the corresponding map. Okay, so that's one way to think about what we've been doing. Now this only works, of course, if we can prove the theorem. And so let me walk you through the details of the proof. Okay, and notice that we need V and W to have an orthonormal basis, but that's always satisfied in an inner product space, right? That's the whole point of the Gram-Schmidt, is that you can find orthonormal bases. Okay, now let's kind of look in detail about what the kth column of the matrix looks like and what the kth row of the matrix of the adjoint look like. So the kth column is given by where the kth basis element gets sent, written in terms of the basis F1 through Fn. And this is where we, Fm, and this is where we use the orthonormal property, right? Because this is equal to TEK F1 times the basis F1, all the way up to TEK Fm times the inner product times Fm. So the inner product of these two. So this is just the fact of using the orthonormal property, right? So this tells me that the kth column of my matrix, right, all of these entries underlined in red become the entries in the kth column, right? So this is TEK F1, the inner product of that, the inner product of TEK F2, and so on all the way down. TEK Fm. So that gives me my kth column. Okay, so now let's go to the adjoint matrix. Okay, on the other hand, the entry in row K, column J, this matrix is given by this particular value right here. It's given by T star Fj Ek, right? Because, and let me write that out in terms of the matrix. So here we'll put this as the kth row, and in the kth row we will have T star Fj Ek, and then we have T star, oh, that should be, yeah, this should be E1, F1, because that's the thing in the first F1. The first column is telling us where like F1 gets sent. The second column tells me where F2 gets sent, and so on. So we have T star Fm Ek. So this is the kth row, and this is the kth column. So now what we want to do is say that the numbers on this row are the exact same as the numbers in this column up to the complex conjugate. okay? And if we can do that, that's true for every row and column. It's saying that one is the conjugate transpose of the other, okay? And to see why that is, let's look at one of these entries on this row. We're kind of looking at the J spot. Well, we can switch the order around by taking the complex conjugate of it, right? So this is the property of an inner product. The order switches around if you can take the complex conjugate. And now we can use the fact that this is the adjoint, so this is equal to TEK J. Okay, so what this means, right, is this particular value right here, I'll write it in red, this is the same thing as TEK F1 complex conjugate, and then the same thing all the way down, right? So this is TEK FM complex conjugate. So what I've written in red, it's exactly the entries right here in the column, but it's all the complex conjugates of each other, okay? So at the end of the day, all right, so let me put a point right there. So complex conjugate. So at the end of the day, what we have are that the two matrices are complex conjugates, are conjugate transposes of each other, which is what we wanted to prove. Okay, so there's a lot going on in this section. Okay, and in particular, the main thing that you really want to learn today is what an adjoint is. You want to know what the conjugate transpose of a matrix is, and then you want to know what the matrix of the adjoint is. So again, kind of make things more simple for you. So when you're thinking of the adjoint, think of it as the linear map you get by taking the conjugate transpose of the original linear map that you're starting with. Okay, so that's where we'll finish for today, and we'll continue on in the next lecture by talking about self-adjoint and normal operators. Have a great day.